طيب بسم الله الرحمن الرحيم. So last time we talked about methods to eliminate routing loops. So we talked about count to infinity. We talked about the split horizon and split horizon with poison reverse. So today, starting from today, we'll start talking about specific routing protocols, specific dynamic routing protocols. So we'll talk about REP, EIGRP, and OSPF until the end of this part. So first, we'll cover routing information protocol with both versions, version 1 and version 2, and then we'll talk about EIGRP after that, and then after that we'll talk about OSPF, depending on the time we have. So starting from REP, REP has some specific features. So the first part of the dynamic routing protocol was just to agree on certain concepts, definition, what routing loops are, what are the techniques to eliminate routing loops, what are the methods, and so on and so forth. Starting from here on, we'll talk about certain protocols, and then we'll mention some of these concepts and definitions as we go, and most of them you should already be familiar with from the first one. So, for example, REP has certain features. The first thing is that it supports split horizon and poison reverse, and split horizon and poison reverse, which are two of the methods that we talked about last time to eliminate routing loops. Also, REP is capable of load balancing, and we said that load balancing, we use it when we have two routes with the same metric or with the same cost. In that case, REP uses the number of hops as a metric. So if the number of hops is the same from two different routes, then we use load balancing, which means that we actually insert both routes in the routing table, and we use these routes to balance the load of the transmitted packets on both routes at the same time. Of course, REP is the easiest to configure because it uses hop count, so we don't have to actually calculate any complicated matrix such as delay or bandwidth. Or you don't have to worry about all of this. It deals with all the links equally. Each link is just one hop, and that's it. Of course, that's not the most efficient, as we have discussed before, but it makes it easy and simple to configure. Also, REP works in a multi-vendor environment, which means that you can have router which is manufactured by Cisco and another router which is manufactured by Netgear talking to another router which is manufactured by D-Link, and so on. The reason for that is that REP is actually an international standard. Okay. So it's standardized. So if you go to IETF website, the Internet Engineering Task Force website, ietf.org, so you will find all the protocols that are internationally standardized, and one of them is actually REP. So REP is international. Unlike EIGRP, as we will talk later, EIGRP is actually proprietary, which means that Cisco actually proposed that as like a de facto standard, but because of the fact that Cisco routers exist in just about everywhere, and it covers maybe like more than 95% of the routers all over the world, then EIGRP becomes like a de facto standard, even though it's not international standard. So these are features for REP. EIGRP on the other side, so REP, unlike REP, which uses periodic updates, as we have discussed before, EIGRP uses triggered updates. Okay, because it uses triggered updates, it uses another, protocol to discover adjacencies or to discover neighbors. So, in order for me to make sure that my neighbor is alive, like I have a router next to me and we have a link connected between us. So if the router goes down, I need to know. So if I have a directly connected LAN, then I actually disconnect the LAN or connect it based on I set the interface on or off. But if I have a router on the other side and we have a link, serial link between us, then I need to know when this router goes down. And the way the routers using EIGRP do that is by using Hello protocol. Hello protocol is not periodic updates. This is not to update the routes. This is just to refresh the fact that all my neighbors are alive. Okay, so it's a periodic message that gets sent by all the adjacencies, okay, by all the neighbors between each other, just to tell each other, I'm alive. That's it. Okay, so if I don't receive this message for a long time, this means that this router has some problem, and maybe it went down. And in that case, I can then update my routing table that this router is possibly unreachable or possibly down, and then I can send a triggered update based on that. Again, unlike RIP, which is a classful, RIP version 1 at least, is a classful routing protocol. EIGRP uses variable length subnet mask, which means that it's a classless, it's by default a classless routing protocol. Okay, so EIGRP is a classless routing protocol, and therefore it supports the variable length subnet mask, which means that the subnet mask gets exchanged as part of the route updates, unlike RIP version 1, which does not use any subnet mask as part of the route updates. Okay, it uses another notion which we did not discuss in the first part, which is called route summarization, which we will talk about today. So route summarization, basically, in a nutshell, is a concept or a technique that tries to group multiple networks in one route entry. So instead of having multiple network entries in the routing table, I can group multiple entries from the routing table and summarize these entries in one line. So this is useful if the routing table goes very large. Then I can reduce the size of the routing table by summarizing some of the network entries. But we have to do that carefully, as we will see in a minute. The use of topology table to maintain all routes, which is another feature that EIGRP uses. So I can. We said that distant vector routing protocols, they do not have complete vision about the topology based on the distance and the vector that we have talked about. Okay, so EIGRP is a special case in that case, and it uses some kind of a separate table, which is totally isolated from the routing table. And this topology table is used to keep track of the topology in the network. So again, the routing table itself uses the distance and the vector and the accumulated cost. But EIGRP specifically uses a separate table to keep track of the topology. It's a classless, as we said, it's a classless distant vector routing protocol, and it's Cisco proprietary. Cisco proprietary here means that it's not international standard, unlike RIP. So it's not like if you have a router which is manufactured by Cisco and another router which is manufactured by Netgear, chances are you cannot use EIGRP. You cannot use EIGRP on both routers because the other router does not support EIGRP because it's only Cisco routers that use that protocol. So first, as we said, we'll talk about RIP version 1, and then we'll talk about RIP version 2, and then we'll talk about EIGRP later on. So some of the So we need to be able to describe the main functions and characteristics of REP. We need to describe how REP version 1 uses or performs automatic summarization, which is something that we need to define and talk about conceptually. And then we need to talk about the recommended techniques to solve problems related to REP version 1, as we said before, which is for routing loops, for example. As we said, this REP version 1 uses split horizon and split horizon with pointers. So the main characteristics, again, of REP, so this is continuing the features that we talked about before. It's a classful distant vector routing protocol. What does that mean? This is very important. We know what classful is, but what does it mean for a routing protocol to be classful? For a routing protocol to be classful, that doesn't mean that it ignores totally the subnet mask. For a routing protocol to be classful, this means accurately that the routing protocol does not use subnet mask as part of the route updates. It does not exchange subnet mask as part of the route updates. So this is what it accurately means, and that doesn't necessarily mean that if we have some subnetworks, okay, we cannot use REP version 1. We can still use REP version 1, but with some limitations, which we will talk about in a minute. Okay? But the most important thing is that REP will never support sending the subnet mask as part of the route update. So we have to find another way based on which REP will be able to deal with subnet mask in the routing table without having to exchange this subnet mask in the route updates. This is count to infinity, so we know that routes that has hop count more than 15, up to 15, this means that this is a valid metric. 16 means that this route or this network is unreachable. Okay? Updates are broadcast every 30 seconds. As we said, we talk about periodic updates, and in the case of REP, it uses periodic updates every 30 seconds, which is pretty long time, but this was valid in the past because of the fact that networks were in nature not very large. In the past, networks tend to have a reasonable size or small size, but of course with the proliferation of the internet and the devices, and now Internet of Things and things like that, nobody actually uses REP version 1 because networks have become really, really large, okay? And your routing protocol has to be extremely scalable to be able to deal with large size networks, okay? So regarding the REP version 1, we talked about the fact that the routing protocol is simply a message format, okay, which is used to send route updates here and there, okay. And then when I receive this message update, I process it and I update my routing table accordingly, okay. So this is the format of the update message, and REP uses a message with, of course, a header and a route entry. One thing to pay attention to here is the fact that the route updates are sent using UDP. So REP uses unreliable transport protocol to send the message updates. Okay. This indicates to us that if the message updates are unreliable, this means that some of these messages may get lost, right? Because it uses UDP. Okay, so that's something to pay attention to. The other thing is that we have, of course, a header. This orange part is the header of the message, and then the body of the message or the route entry. If we look here, we see that the route entry itself, the route entry part, may get as large in size as 512 bytes, and that can carry up to 25 routes. Up to 25 routes, which means is that the router will group all the routing entries in the routing table, okay? And if the number of these routing entries is more than 25, then I have to split them using 2 or 3 or 4 messages of these, okay? So first I use unreliable transport protocol, and then I group the route entries in the route entry part. After I fill the header, I group the route entries in here with up to 25 routes in one message. Okay. So the header part is basically 3 parts. Okay, you have the command, you have the version, and you have 2 bytes which must be 0. And as we can see here, in the header part, there are 2 bytes which must be 0, and here there are 3 times 4 bytes which must be 0. That's an observation, and someone might ask, I mean, what is the point of having all this size of bytes which must be 0? What is the point of having them? The idea of having this, because this idea happens in many protocols, even IP, TCP. In many cases, they use some of the fields must be 0. The idea here is that we are trying to make the protocol expandable or extendable, okay, in the future without having to change the message drastically. So, for example, if I have 2 bytes must be 0 and these 3 bytes must be 0, if we have rep version 2, okay, rep version 2 introduces new concepts and new techniques which are not addressed in version 1. But in terms of message format, rep version 2, all it needs to do is just to put more fields in these entries here. Okay? So that facilitates the fact that if I send rep version 2 message to a router which uses rep version 1, then what will happen? The rep version 1 router will still accept the message, will ignore these fields, okay, and will take the entries which make sense only for rep version 1, which indicates that if a router supports rep version 1 and another router supports rep version 2, okay, if they talk to each other, then they will revert to using a rep version 1 without having to, but they will understand each other. They will still understand each other, but they will talk using rep version 1 because the router that supports rep version 1 will ignore all these fields. They will still be there, which means that in terms of format, it will understand everything, but it will ignore these fields and only process the fields that make sense for rep version 1. So this idea or concept is used in many protocols really. So they try to make room for future expansion of the same protocol, and that's what happened. Rep version 2 came later, okay, and it started to use some of these fields, and it actually filled most of these must be 0 fields with new information and new entries without having to change the structure of the message. Okay. Okay, so first we talked about the header. The header has 3 fields. 2 fields of them are filled with something. the first field, or the first byte, has 1 or 2. 1 to indicate that this message is a request, and the 2 indicates that this message either is a response or update. Okay, and we'll talk about the two types of commands. Version, of course, to indicate whether I talk version 1 or version 2. Okay, so version here indicates the rep version number, whether it's 1 or 2. The route entry itself has all these fields, and the first 2 bytes indicate the address family, which in 99.9999% will have a value of 2 to indicate that this is the IP address family. And as we know that there are some other network layer protocols other than IP, right? There is like BSD and there is other types of protocols. Of course, IP is the predominant by far, okay? But rep, because rep is actually very old, from the days of BSD and other routing protocols or other network layer protocols, rep was there and was being used, and that's why here you have to indicate which address family we're talking about. So if that has a value of 2, so all you need to do is just each routing entry is simply 2 things: the IP address and the metric. Those are the only 2 fields in any route entry. As we said, no subnet mask. We cannot communicate subnet mask here because rep version 1 is classful. Okay, so rep version 2, for example, because it's classless routing protocol, it started to communicate the subnet mask in some of these must be 0 fields. So it started to consume some of these fields to communicate the subnet mask. But rep version 1 is classful routing protocol. It does not exchange subnet mask as part of the route updates. Okay. Then this route entry will be replicated as many as we need, up to how many? 25. Up to 25 route entries. We cannot accommodate in one message update more than 25. So if you have more than 25 route entries in the routing table, then we have to use 2 messages or more than 1 message. Okay. So as we said, rep uses 2 types of messages. One is the request, and the other one is the response or the update. So the request message here is sent during startup. So when you start rep version 1 usually starts by sending commands to all the neighbors to tell them, give me your route updates. So this is the only time that it's triggered. You actually request the route entries from your neighbors. So this happens one time at startup. After that, then all the routers will communicate the route updates using response message, which means that in the command field in the header, it will have a 2. It will have the value of 2 to indicate that this is a response. So only at startup that rep A sends a request message to all the neighbors to request the route entries from all of them. Then what happens is that the router, when it starts up, it sends the request message. It receives what? It receives message response, which will contain all the route entries in these routers, in these neighboring routers. It will process one of them at a time. It will process each one at a time, and then it will update its own routing table. After it updates its own routing table, then it sends another route response or message update to all the neighboring router. Okay, with its own routing table, including the networks that are connected to it. In order to make sure that you understand this, So if we have router R1 is starting, okay? So when router R1 starts at the beginning, of course, you have connection between router 1 and A and router 2 and router 3. So router 1 will send a request to router 2 and a request to router 3. This is a request message. So that's number 1. Okay? So this is at the beginning. So this request will force router 2 to send a response message. And this response message will contain all the route entries in the table. Okay? Of course, here R1 has some direct connected networks. Okay? So when router 1 receives the response from router 2 and router 3, it will update its own table with all the entries that it received from router 2 and router 3. Okay, so this is number 1. This is number 2.
It will update the routing table
of its own, of router 1.
And what are these lines?
These lines, these indicate that these are directly connected networks, LANs connected on router 1.
Does it mean other router?
No, LANs, directly connected LANs. They don't have to be connected through other routers. Direct LANs, LANs. Yeah, connected on a switch with some PCs. There are some PCs here, and all these PCs are connected on this router. Okay? So when router 1 receives these responses, it will update its own routing table. So this is routing table for router number 1. Okay? After it finishes processing those, then it sends another update message or response message in a third step. Okay, so first step, request. Second step, response from all the routers that receive that request. Third step is the response from router 1 to both routers. And this response at the third step will contain the routing entries in the routing table of router 1, including the LANs that are directly connected to router 1, because router 2 and router 3 until now do not know any information about these directly connected networks, right? Yeah, these directly connected networks, only router 1 knows about them, right? So at the beginning, router 1 will receive responses from router 2 and router 3, will update the routing table, and then will group all these entries, which will include information about the directly connected networks, and then will send them into router 2 and router 3. So router 2 and router 3 will update their entries with the directly connected networks that are connected to router 1. This is at startup. Later on, all we need to do is that every 30 seconds we send message update as normal. Okay? So the message update here, the response message will contain the routing table entries. Okay? Okay, so as we said, RIP version 1 is a classful IP address, is a classful routing protocol. And what this means is that we as far as the route updates are concerned, okay, all the IP addresses that are exchanged as part of the route updates, they are by default to us, they are classful addresses, which means that from the first byte, we know the class of the address. Based on that, we can deduce or we can extract the subnet mask. What is the length of the subnet mask? For example, as we all familiar, if the first byte is from 0 all the way to 127, this means مش حدش فاكر طبعا class A. Okay, from 127 all the way to 172 or something like that, this is a class B. From 172 to 196, this is class C. Okay. So if we are class A, this means that the first left byte is the subnet mask, which means that the subnet mask is 255.0.0.0. This is subnet mask for class A all the time. Okay. If it's class B, then it's 255.255.0.0. And if it's class C, then there are 3 255s and then 0. Okay? So these are the classful addresses. These are the classful addresses. Classful routing protocol means that we do not. This is the definition of a classful routing protocol. Okay? That this routing protocol does not send the subnet mask as part of the routing updates. This is very important. This is not to say that we never deal with classless IP addresses. Huh? This is not to say that classful routing protocol will never be able to deal with classless IP addresses. We didn't say that. We just said that classful routing protocol is not capable of sending subnet mask as part of the route updates. You deal with it in any way you see appropriate, but I'm not going to send any subnet mask as part of the route updates. So we'll see that REP version 1 still uses classless IP address, but it doesn't. It has to use certain logic to try to interpret the subnet mask, okay, even though it's not by default in the route entries. Yani the subnet mask is not in the route entry. So when REP receives the route updates, it should try to interpret or to get it somehow, to guess what is the subnet mask in case that the IP address in the route update is classless. It uses classless address. Okay. So this is a typical example of a network that uses REP version 1. So we have here 3 routers. Okay, the 3 routers are connected using serial interface, serial PPP or serial link. Okay, and these are the addresses as you can see here, and all these addresses, luckily, they are classful addresses, which means that all of them use 192, and 192 is class C. So without any thinking, I know that the subnet mask is /24. And it happens that indeed the subnet mask is /24. So here, REP does not have to do any intelligence because all the addresses are by default classful addresses, so it's going to be fine. Each router has one connected switch with possibly some PCs, but we don't have to talk about PCs. For us, it's a network with a network address. And here, for example, the network address is 192.168.3.0. This is the network address. Again, you need to review and refresh your memory with all the concepts about IP addressing and subnetting and all of this from 455, because this is very, very important. Okay, so it uses 5 different subnets, of course. We have one subnet here, which is 192.168.3.0, and we have here .4.0 and .2.0. These are 3 subnets so far, and there is one here which is 1.0 and 5.0. So we have from 1 all the way to 5. We have 5 subnets. It happens that all of them use classful IP addresses, which makes the whole topology clean and no need to do any special things. So rep will be able to deal with this natively without any special handling. Okay. So in that case, the routing table here, as we can see, the routing table contains subnet mask. Okay, so does that comply with the definition that we said? It does. It does, because we said that classful routing protocol does not exchange subnet mask as part of the route updates. We didn't say that it does not use subnet mask as part of the routing table. Using subnet mask as part of the routing table is a must. Okay? But this subnet mask will have to be deduced, will have to be interpreted somehow. So rep will get this easily, right? Because it knows that this is class C, so it will put in the routing table the class C subnet mask, which is a /24 or 255.255.255.0. And because all of them are class C, so the subnet mask is the same for all of them. But when it sends the route update, when router 1 sends the route update, it will group only this IP address and the hub, the number of hubs. Okay, so R1 has these 2 subnet masks. For R1, you have this and you have this. These are neighbor networks. These are the directly connected one with this subnet mask. And R2, of course, has 3 subnets, and R3 has 2 subnets. So when they start exchanging this as part of rep, so what you do is that you say router rep, or you start rep, and when you do that, each router will send requests to all the neighboring routers to ask for the route entries using the request message, as we said, which happens at startup. So router 1 will send to router 2, router 3 will send to router 2, okay? And then router 2 will send to router 1 and router 3. So each router you start, it sends a request at the beginning and asks for route entries from the other neighbors. And then it updates its own table, and then it waits for 30 seconds to send an update. When you start rep, or when you say router rep, you have to also specify which interface you want to use as part of exchanging the route updates. Okay, for example, router 1 needs to receive and send updates on this side, okay? And router 2 here needs to send and receive updates on those 2 interfaces, and router 3 needs to send and receive updates on this interface. Once you specify these interfaces, then rep will take it from there, which means that it will start exchanging the route updates until conversions happens. And even after conversions, it will still send route updates every 30 seconds, regardless whether there is conversions or not. So the first thing, we start rep, and then we specify which interfaces we need to use for exchanging route updates, and then rep will send the request on this interface to ask all the neighboring routers about the route entries, and then we'll start exchanging the route entries with all the neighboring routers. So that's how it happens. So we say router rip. One important message here is that you're not asked to memorize any of these commands. Okay? So don't worry about the format of these commands. You should never get into questions that asks you about the format of the command and so on and so forth. You don't have to memorize that. This is just to show you an example how you start it up. So router 1, for example, will start router rep, and then will say, I want to send message updates here and there. So I want to exchange message updates on these two subnets or these two addresses, which will activate this interface and this interface. Same thing on router 2 will send here, here, and here. And then router 3 will send here and here. Once you do that, then rep will start advertising the network updates regularly every 30 seconds. Okay, so now we talked about the concept of automatic summarization. This is a very important concept, as we said, that we can use to save quite a bit of overhead exchanging route entries. So we can reduce the size of the routing table drastically by using automatic summarization. But as we will see, rep has some limitation when it comes to automatic summarization because of the fact that it uses classful routing protocol, or it does not exchange subnet masks as part of the route updates. So we have modified the scenario that we talked about because we said that this scenario has all addresses in the same class C, 192, and all of them are classful addresses. So the subnet mask is easy to interpret or easy to guess. So the subnet mask will be /24 for all of them. So we have modified this scenario slightly. So now we have part of the network here. If you notice this part here uses 172, which is class B. Okay, and then this part uses 192, similar to the previous scenario, and 192 is class C. So we have the subnets that we talk about here is 172.168.1.0. These are the subnets, and remember that this is class B. Okay, however, the subnet mask is 24. So this indicates that this address is a classless address. If we deal with it as a classful IP address, then we have to use /16 because it's class B, right? But the major network 172.30.0.0 has been subnetted or subdivided into 3 different networks. So these 3 different networks has 172.168.1.0 and هنا .2.0 and هنا .3.0 /24. So these are subnets under the major network, which is class B. Okay? So these IP addresses are in general classless IP addresses. So if we do not deal with these as classless IP address, if we want to deal with them as classful IP address, then we will have to chop the 1.0 and do 2.0 and 3.0 by default and make the subnet mask a /16. Okay? So the question here is that how rep will deal with this. So as we said, we have 5 subnets. We have in general 5 subnets here, but 3 of these subnets can be grouped under classful address, which is 172.30.0.0 as a class B address. But if you subdivide this into 3, then it becomes 5. 1, 2, 3, 4, 5. فهمنا السيناريو ازاي؟ So we have 3 major networks, 3 major classful networks. Okay, one of these networks has been subdivided into 3 subnets. But when we subdivide this into 3 subnets, we have to now use a subnet mask which is not /16 because we subdivide a major network. Now you have to use a subnet mask with more ones. We have to, right? So here we subdivide this into 3 subnets with subnet mask /24. So these subnets are part of this classful network address. So the question is now, how can RIP version 1 deal with addresses such as these, even though it cannot send subnet masks as part of the route updates, as we said, right? So RIP uses what we call automatic summarization, and automatic summarization defines a very important rule, which helps you to guess, okay, or to deduce the subnet mask from the route update, even though you don't have the subnet mask explicitly in the route update. Okay? So I don't have the subnet mask as part of the route update, but I will try to guess it. So automatic summarization or RIP in general use certain rule which helps you to get this subnet mask even though it's not in the route update. So the rule automatic summarization, what it will do is that it will try to group all these 3 subnets, okay, into one network which is 172.168.0.0/16. In order for this to happen, we have to have what we call a boundary router. So this router 2 is now called the boundary router. Why? Because it's the limit between all the grouped subnets and the other part of the network. Okay? This is the interface, or this is the boundary between all the grouped subnets, because here we have 3 subnets, right? 172.168.1.0.2.0 and .3.0, right? And R2 is the boundary that connects all these subnets with the rest of the network. Okay? So we call this a boundary router. Why? Because what will happen is that inside these subnets, the route updates will have to be detailed. Which means that we have to have 172.168 or .30, sorry, .1.0 or .2.0 or .3.0. When router 2 advertises these networks to the rest of the network, it will advertise one route entry. It will group all of them into one route update or one route entry, which is a 172.30.0.0/16. Okay? So router 2 will advertise all these subnets in one entry. which indicates what? If you want to send any packet to any of these networks, you have no way but sending it to router 2, right? Router 2 will then take care of branching this packet into here or here or here. Okay? So it's like you have grouped this into one LAN or one network. Okay? And you have to send to this subnetwork through router 2. Router 2 will then take care of sending this into one of the subnets underneath. But all the other side of the network does not have to deal with the details about these subnets. It doesn't have to know that in order to send to 172.30.1.0, it has to send to R2. If it wants to send to 172.30.2.0, it has to send to router 2. If it wants to send to 172.30.3.0, it has to send to router 2. So it makes sense to group all the three of them into one entry, which is a 172.30.0.0/16, which complies with the fact that this address is classful address. So it will make sense to group all of them into one major network, which is classful address, which is in that case 172.30.0.0. So this is the concept of automatic summarization in general. So we try to group multiple entries into one entry. But in order for us to do that, we have to designate what we call a boundary router. And a boundary router is the router which is used to summarize all these entries into one entry and send it to the rest of the network. Okay? So to automatic summarization to know how the different routers in fact perform this automatic summarization. We said that router 2 will have to have in the routing entries all the three subnets, right? When it sends update to router 3, only then it will send one route entry, which is 172.30.0.0. Okay? Inside these networks, for example, in router 1 will still use separate route entries for each of these subnets. Okay? We'll still use separate entry to send to R2 and to send to this LAN and to send to R3 through 2 hubs and so on. It will not summarize anything because it's not a boundary router. R1 here is not a boundary router, so it will have to have all the entries. Router 2 is a boundary router, so it will have separate entries in the routing table, but when it sends the advertisement, the route update to router 3, it will use automatic summarization to group all of them in one entry. So inside this 3 subnets, as we said, I have to have separate entries in each router, okay, even the boundary router. Automatic summarization only happens when the boundary router sends the route update to the rest of the network. Only then it will group the 3 route entries for the 3 subnets into one classful address. Okay? So if we look at the routing table of router 1, if we look at the routing table for router 1 will have one route entry for a network which is 172.30.1.0, 172.168.1.0/24. And it will have in the routing table explicitly an entry which is like 172.30.1.0 with a subnet mask of /24 in the routing table. Okay? How does it know the subnet mask of this network? Well, this is given because this one is directly connected, remember. The subnet mask of this is given to router 1 when, well, we have to specify it. Remember when we said router rep, we have to say that on this interface trigger the updates or start rep, so we have to specify 172.30.1.0/24. So router 1 knows the subnet mask on all the interfaces that are directly connected to it. Okay? Type. So router 1 will have in the routing table this address with subnet mask. Will have also 172.2.30.2.0/24 because this one also is directly connected to it. Okay? And it will have route entry for 172.30.3.0 using one hop to R2. Okay? And this one will have to be communicated from router 2. So router 2, when it sends to router 1, it will send an entry for this, which then R1 will insert into its own routing table. When router 2 sends to the remaining part of the network, it will summarize this into one entry. It will summarize all these three subnets into one route entry to router 3. How? This is the rule here. This is the rule, and this is very important now. This is very important to understand. Automatic summarization happens using this rule. What will happen is that if a routing update gets sent on an interface such that the subnet of that interface, remember, if this interface, what is the subnet of this interface? It's 172.30.2.0/24. Okay? So, if router 2 sends the route entries to router 1, okay, then it will send the 172.30.3.0/24. Right? It will send it to router 1. Router 1 will then ask itself. Remember that when I send this route entry, I do not send the subnet mask. I will send only what? 172.30.3.0. I don't send the subnet mask. صح؟ طيب. How does router 1 interpret or guess the subnet mask? It will apply this rule. The rule says simply, if the subnet of that interface, okay, and the subnet of this interface, of this entry, are under the same major network, then use the subnet mask of the interface for this entry. Again, how? So this interface now is 172.30.2.0, right? And I received an entry which is 172.30.3.0. Okay? So the question here is that, are these two subnets are on the same major network? Well, the answer is yes, because both subnets are on the major network 172.30.0.0, right? So in that case, what router 1 will do, it will accept this entry 172.30.3.0 with a subnet mask of the same subnet mask of the interface, which is /24. Because it does not have this subnet mask as part of the route update. So the rule here is that if the route entry has the same major network of the interface, then I will put it in the routing table with the subnet of the interface. But if R1 receives a route entry, for example, for this network, يعني ركز معايا, for this network, let's see, it will receive a route entry which is 192.168.5.0. Will it receive a subnet mask? No, right? It will not receive a subnet mask. So this entry came through R2, of course. So R2 will send a route update which will contain an entry 192.168.5.0. R1 will ask itself, does this route entry exist on the same major network of my interface? No. So I will use the class of the incoming route entry as the subnet, which happens in that case to be /24. Okay? So that's how it works. If I receive a route update with a route entry, and this route entry happens to exist in the same major network of that interface, then use the subnet mask of that interface for this route entry. Otherwise, if the route entry has a subnet which does not exist under the same major network of my interface, then use the subnet based on the class of that entry, which in that case it's class C. So the subnet mask will be 24. So this automatically indicates what? When router 2 sends route entry for 172.30.3.0 or 172.30.1.0, it will send it to router 2. صح? Router 3, sorry. Router 3 will then apply the rule. The rule says these route entries do not exist in the same major network of the interface. صح? So in that case, I will use the class of the address as the subnet, which means I will put an entry 172.30.0.0/16 because it's /16. This is the class of the address, right? And this will help summarize the entry. So whether you receive an entry 172.30.3.0 or .2.0 or .1.0, for you they are the same, because all of them do not exist in the same major network of that interface. So you will accept all of them as one entry. Okay? So you will accept all of them as one entry. So that's why it's called the automatic summarization. Using one simple rule, you can perform automatic summarization, and you can benefit from the concept of summarizing multiple entries in one route entry in the routing table. Therefore, you can save the size of the routing table. Of course, the implication of this is this explains this scenario using the commands. As we said, we don't have to memorize the commands or to know how to display the routing table using commands and stuff. This is not what we need to focus on. But this is just to give you some indication that router 1 will indeed accept the 3 entries here. Right? Because the 3 entries are coming on an interface which exists in the same major network. So I will accept these entries and I will use the subnet mask of the interface, which is /24. So I will accept these 3 entries. Router 2, of course, is a boundary router, so it will also contain the 3 entries. Only in router 3 here, you will see here, router 3 has 1 entry only, which is 172.30.0.0. Why? Because it received multiple route entries from router 2. All of them are not in the same major network of the interface. So I will summarize them. So router 3 here has 1 entry. Major benefit of this is that the size of the routing updates is reduced, of course, because in that case, router 3, from router 3 onward, router 3 does not have to send all entries about all these 3 networks. It only has 1 entry which summarizes all these 3 subnets. So it will send only route entry corresponding to all these 3 subnets. So this way, I have saved some resources and I have saved some size for the route updates. And also, I saved a lot in terms of routing table, which will make the lookup faster, right? So when the size of the routing table reduces, then you can look up the route entry faster in that case. So that's the concept of automatic summarization. One thing to notice here is that you have to be really careful when you design your subnets. Okay, because if for example you have a different subnet here, like for example, instead of using 172.30, use 172.31. Okay? In that case, you cannot group the 3 of them into one major network. So all these 3 subnets, they have to be under the same major network. If you assign a subnet in the middle which is different, this is what we call discontiguous networks. They are not continuous. They are not all under the same major network. So in that case, you cannot use automatic summarization correctly. Automatic summarization will fail in that case. So that's one of the limitations for REP version 1. Because of the fact that it uses classful routing concept, it does not exchange the subnet mask. So because I cannot exchange the subnet mask, I have to invent this rule, okay, in order to be able to guess the subnet mask even though it's not in the routing update. But I can trick this rule very simply by making one of these subnets different. So in that case, it will be very tricky for automatic summarization to work correctly. So if you want automatic summarization using REP version 1, you have to be very careful when you design your subnets. Okay, that's a very important issue here. So we'll stop here, inshallah. We'll continue next time.